everyone. My name is Dhananjay. I'm a software engineer here at LinkedIn. I'll just give a quick introduction to the speakers. They'll give you, more of a full introduction of themselves when they come up here. But I'm going to be giving sort of an overview, just from a high level of, what is LinkedIn and how do we use Scala, Java, some of the other languages that are here. Mark Pasquale is going to talk about how Scala is used in LinkedIn today. Joshua Ehrlich and Ray Wang are going to talk about how Scala is used in the social graph. And Joel Kashi is going to talk about Kafka. Okay, so first of all, how many people have a LinkedIn profile? So it seems like most people know what LinkedIn is. It's the professional network. And our mission is to connect the world's professionals to make them more productive and successful. And a lot of the features that are on the site are really geared at that. And so, in terms of Scala use, at least my view on how I've used it and how a lot of feature teams could use it, is in terms of sort of a drop-in replacement for Java to create the same sort of features on the site that you could in Java. This is just some stats on LinkedIn. Hopefully these are up to date. There are about 161 million members worldwide now, and about 82% of Fortune 100 companies use LinkedIn to hire. And looks like we've got about 2 million company pages as well. Okay, so an engineering overview. One of the interesting things about LinkedIn is that it is pretty much a JVM stack, in that our front-end web apps are deployed in Tomcat, and we have a lot of back-end services that are deployed in Jetty. And we view ourselves as a services-oriented architecture. So a lot of those services have Java interfaces and Spring remoting using serialized Java objects to communicate between different services. And we're moving towards a more RESTful approach, so moving that to being REST and Avro instead. But right now we're sort of in a mixed environment. And because of that JVM stack, you do have the ability to write the code for your service in Scala, Java. There's actually some use of Clojure as well. And because of that, there is this mix of languages. Groovy, JRuby, Scala, it's all sort of mixed in there. In terms of overall amounts, by and large, it's pretty much a Java shop, right? Like the vast majority of the code is Java, and Scala, like in terms of comparison, I think I have a stat here about 7 million lines of Java code and only about 85,000 lines of Scala. And this is sort of a distinction from maybe some other companies where there's sort of a rule like, everything's in one language. That's actually one of the really nice things about working at LinkedIn is it's a little bit more maybe like a federation of states, in that there are a lot of different departments in engineering, and there are certainly some things that are done from the top down, so everyone does it in the same way. And that's great for being able to deploy services and be able to look at other code. But we do have sort of a culture here of allowing experimentation, which is really good for developers. And so the idea is that feature teams are relatively free to explore the sorts of technologies that they want to use. And whether that's Java, Scala, Clojure, that's great. And the idea is that if they're successful, then these sort of best practices will rise up and be adopted by other teams. One sort of shining example actually is not even related to the JVM. It's our mobile team's use of Node.js. Many of you have probably seen a lot of press about that and how successful the mobile team has been with Node.js. And that's a great example of the fact that within LinkedIn there is a lot of interest in different programming languages, and people sort of use the right tool for whatever job it is that they want to do. We also follow a trunk development model now, which is great for this process of in general being able to get your code out really soon. In terms of having a whole bunch of checks that run pre-compile checks, sort of a short post-commit check, much longer checks, and being able to deploy services and roll them back in sort of a really consistent way. And so if you're writing Scala code and you're fitting that into the rest of the framework, it all just sort of works, and it's kind of nice to give you that freedom to explore. So I work in a department called Content and Community. It's really responsible for the more engagement-focused areas of the site, things like the LinkedIn inbox, or groups, or the network updates, and LinkedIn Today as well. And the way I've used Scala primarily has been as just a drop-in replacement for Java. To me, it's just a much better Java, right? Because there's so many features in the language that just make coding more of a joy compared to what you can do in Java. And of course, if many of you are familiar with Scala, you know this in terms of case classes, tuples, function literals. There's so many things that just make it much easier to write more concise code with less boilerplate that's easier to read. But all of that code could be written in Java, right? In terms of fitting in, to build some specific feature on the site, you could have used Java, and it would be fine. But what I found in practice that I've gotten a lot more satisfaction in terms of productivity from writing code in Scala. A lot clearer code, so it's easier to look at it and see what it's doing. And then also the use of the Scala REPL, which has been a real productivity boost for me in my sort of day-to-day programming. And so I won't show any code examples because, oh, the organizer's cell phone. Yeah, so Mike did that. That was actually planned. Mike did that as an example that everybody should turn their phone off, right? So some of the other talks are going to show some of the projects that LinkedIn is open source, and so there'll be a lot of code snippets there. So I chose not to show any code snippets from the stuff that I'm working on now, especially since some of it's sort of in flight and it's not really public yet. But what I will show is sort of one example of using the Scala REPL. And I think for a lot of people coming to Scala, initially that's probably one of the places that you should start. Because in terms of saying, like, how can I get a productivity boost out of Scala, even if you're programming in Java, you still can. And it's really immediate and really helps with anyone trying to move to Scala as well. So the way I've used it here is in a number of ways. One, connecting to live services, because services are, whether they're talking Spring remoting with Java interfaces or they're talking REST, you can just fire up the Scala REPL and connect to it and be able to make calls. And this slide, I don't know how readable it is, but this is an example of something that I did in order to find out what was going on for a particular question that came up in production. And essentially, believe it or not, I just kind of fired up the Scala REPL and sort of typed this in. And there's one service that was using Voldemort. Many of you are familiar with Voldemort. It's this sort of distributed, key value store database that LinkedIn has open sourced. And I wanted to find out, wanted to be able to query that database to find out what was going on with some data. So very quickly, you can see from this, it's kind of, maybe it's a little messy and there are no comments or anything, but believe it or not, I just typed this into the REPL and boom, I got the answer of what I wanted. Which to me it falls into that area of productivity and things that you can do without even writing a lot of Scala to just get sort of immediate benefit. So the Voldemort database was there, and I just wanted to find out for a given set of members what buckets they fell into. So the data in the Voldemort database was sort of keyed by, I don't know if the laser pointer is on this. Actually, it's probably safer not to use this, but essentially there were a number of keys that were constructed based off of a time zone, either weekly or daily, and then the time zone offset, and then there's basically a list of member IDs. And there were particular members that I was curious about as to what buckets they had fallen into. And so I was just able to fire up the REPL, type this in, and boom, get my answer from from Voldemort. And so that's basically. Oh yeah, okay. We'll take questions now, and then after that, Mark will come up and talk to you about LinkedIn Today. Oh, and please go to the mic for any questions.
Get config. Why do you have two configs in the name?
That's actually the Voldemort Java API, and so this is a good example of something I do all the time with the REPL is playing around with Java APIs. Whether it's figuring out how something in Jota time works, or figuring out something with the Voldemort Java API. You're talking about val config equals new client config. That may be a typo in the slide. Yeah, so copying from Notepad into PowerPoint. But yeah, actually the Java API is new client config. And that's nothing Scala about that. That's just the Voldemort Java API. Okay. If there are no other questions, then Mark Pasquale will talk to you guys about LinkedIn today.
Hi everyone, my name is Mark Pasquale. I'm a software engineer, just like Dhananjay, at LinkedIn, and I've been actually working here for almost exactly a year now. I had heard about Scala before I arrived at LinkedIn, but had never had the opportunity to actually use Scala in my previous jobs, and it was something that I always wanted to explore. But the opportunity came to me pretty much as soon as I got to LinkedIn. I actually inherited some of Dhananjay's code as part of LinkedIn Today, which I'll talk about. In addition, I think Ishai Smith sitting there, he also worked on some of the code that I'm going to talk about today also. So LinkedIn Today is, well, first of all, how many of you actually have heard of LinkedIn Today and that part of the website? So not too many, but basically it's the part of our website where we display news for you so that you could become a better professional. Basically the news you need to know about your profession on a daily basis. So as it says here, your essential source for business intelligence. I don't have enough moxie to use those terms, but yeah, essentially that's what we're trying to do. LinkedIn Today, we allow you to customize the things that you're following. Any topics you're following. Let's say I'm a computer software guy, so I should be following computer software, and I'm automatically followed into that. But there might be other things that I like that I can follow, like real estate or whatever. So you have the ability to do that, and we'll present to you news that other professionals in your industry have acted upon, basically. So that's how we drive the relevance there. So what are some of the things that we use Scala for on LinkedIn Today? And I'm, again, like Donna just said, I'm not going to get too technical with the code snippets at all because this is not an open source project or anything, but I'll talk to you about some reflections on it after. Part of what we use Scala for is news fetching, and lo and behold, Ishai wrote most of this code. Basically, we use the news fetcher to grab RSS feeds from a lot of different places so that we can have more content that we can go through to pick relevant articles from so that we can present it to our users, right? So we go off, we scrape these articles, grab data about them, and then use it to drive relevance. Without this, we wouldn't have that many articles to begin with because we're relying on people to basically share stuff on our site or read articles on pages to actually get that. But with this tool, we actually are able to grab a whole lot more articles from which to drive relevance. And this is, in addition to being used on LinkedIn Today, it actually is used to drive company news, some groups content, and other things on the site. So the question is, how did we use Scala in this? Basically, the LinkedIn Today itself is a mixed Scala Java, and Scala and Java, as maybe not many of you know, they actually play really well together. There are some caveats there, but most things are pretty straightforward. And the specific thing that we used from Scala for the news fetching were the actors to get us concurrency. So an actor was basically spawned, was used to grab the articles, each article from an URL, and using an interceptor pattern. So basically, there's no shared state between the different fetches, and messages were being passed, so it was easier to manage the concurrency using the actors. In addition, we also used it to write a very simple caching layer for our URLs and redirects. That was actually a very cleverly written piece of code by Ishai that I had to look into the other day, and it was fine, Ishai, so it's good to know. And we also heavily use it for testing. it drives a lot of our testing. Okay, so that's news fetching. And then the code that I inherited and modified from Don and Jay is here, the LinkedIn Today emails. And we basically will send you a digest of email daily or weekly based on your interests. So if you're, interested in computer software, real estate, whatever it is, we'll blend these articles together using our relevancy model and send you a digest of these every morning or every week, depending on your preferences. Or, of course, you can always turn it off. So let's see. Let's go into a little bit of details here. The Scala use on this is actually very heavily Scala. There's, like Don and just say, we actually use this as more of a Java replacement, a drop-in. So it was pretty heavily Scala, and this was actually the first project I worked on, so it was a kind of a dive into Scala at that point. The way that it works, it's a batch processor that will pick valid batches to send emails for. We used it to talk to Voldemort, like Don and Jay kind of explained using his REPL example. We used kind of the same thing. We talked to Voldemort through a data access layer written in Scala. And we actually built a state persistence model for when the service, sometimes they crash or whatever, they come back up, make sure we aren't sending you emails more than once a day or once a week as your preference state. And we actually built that on top of Oracle, and that was written in Scala also. And this is completely integrated within our JVM stack. So those are two of the uses. So what did I learn from Scala and from using Scala on these projects? I don't consider myself an expert at Scala at all. I'm a solid intermediate, maybe. So a lot of my daily job is in Java. And I can tell you some of the things that I learned right away. One, you can write much more concise code in Scala. You can also write code in Scala that is as verbose or even more verbose as Java. It just depends on your desire, I guess. We also try to use a functional style, which helped deliver higher quality code. It was a lot easier kind of to read with the immutable state. It's a lot easier to reason about things. We use pattern matching very heavily, which is pretty cool. If anyone hasn't checked out what Scala has to, with regard to this pattern matching, I would go do that. The actor model was actually really good for concurrency. And my personal favorite, higher order functions, just the ability to pass stuff through to like the map function or whatever it is for each or whatever. So the cons here. Brevity versus readability. Again, it's very easy to write some Scala code that is very concise, but whether or not the person who comes and maintains it after you understands it, that's up to you to help comment with that or to use stuff that is easier to read. Now, given that we're in a kind of a mixed Java Scala environment and it's very heavily very heavily Java, if you write very kind of extremely concise Scala code, maybe the next person to come along won't understand it. And I've actually found that this to be somewhat of a problem in our own group with regard to not all of us are on Scala, are programming in Scala. So in a mixed environment, that's something that we had to take into account because the learning curve, relating to the next bullet point here, the learning curve is kind of steep. It's not something to take lightly. You can kind of get into it without really doing too much what I'd consider more advanced Scala, so your code looks the same between Scala and Java, but then you aren't really taking advantage of some parts of the language, right? So it's really up to you, to you and your coworkers to decide on a good style that everyone's going to be able to read. People that are coming over from the Java world will still be able to kind of deal with. So there's that, and then critical mass adoption. We're not like Twitter, where Scala is everywhere. We're very much still a Java house. So we have to keep that in mind when people are going to maintain our code. Like it would be fine if I was the only person who was going to maintain this code. But you know what? I'm going to leave LinkedIn someday. and then someone else is going to have to deal with it. And they'll have to deal with it, on the learning curve that Scala has. And another con is the fact that there aren't that many, like, at least in my opinion, there aren't good tools for this yet. Like the IDE support for this is not really there for me. Some people might have different opinions, but I use Eclipse, and it's not really that integrated, but you can get by. So it's something else to consider. So basically, that's pretty much it. Any questions? No questions? So if not, I'll hand it over to Josh and Ray to talk about the social graph.
Hello. So, as mentioned, I'm Josh Werlick. This is Ray. We work on LinkedIn's social graph team. I've been here for about 9 months. Ray's been here for
almost 4 years.
Almost 4 years, yeah. So we use Scala fairly extensively. So the social graph handles sort of all of the entity relationships. We do sort of intelligence, like checking distance, figuring out who's connected, this type of thing that you'd want to know with a social graph. I'm going to talk a bit about Norbert, which is an open source project that people on my team wrote. I actually have not done very much work with it myself. It was mostly written by our boss, Chris Conrad. But it's open source, so I can show you code snippets, and it's nice, and there's some very cool Scala features in that code. The distributed graph itself is also heavily Scala. Some of the other services we have on top use Java as well. But most of the new code we write these days is Scala. And we use a lot of features from Scala because they're fun. So generic classes we take advantage of, type bounds, case classes, sealed classes, these types of things to make the code concise, to make it readable, easy to use. Traits and mix-ins give you a lot of code reuse. They're very nice. I personally, along with Mark, really like higher order functions just for the ability to sort of reason about the way they're going to work, make things very simple. Sometimes it's very easy to parallelize map calls, for example. So that's nice. To make concurrency easier, we use a combination of actors, particularly in Norbert, and copy on write, which Ray will talk about in the actual distributed graph. And we use a lot of these Scala collections. And so some takeaways that we've found, it's concise code. It makes the coding easier, it's cleaner. You have more code reuse. You don't have to have all these boilerplate that you would have if you used Java. One of the disadvantages, which Ray's going to discuss in more detail, when you use these high-level Scala collections, sometimes it's hard to reason in performance-critical areas, and it can make a big difference. So I'm going to talk a bit about Norbert. It's available on GitHub. We used it off the LinkedIn SNA branch. There's the original one, which is under Chris Conrad's GitHub, R Haven or something of that sort. But most of the changes now have been on this one. So it's a Scala library, and it's designed to handle cluster management, do cluster-aware client-server networking. We use it to partition the social graph, distribute requests across machines. And it's built using Zookeeper, Netty, protocol buffers. So let's dive into some of the code snippets. So one of the things that's used heavily in our code, both in this and in the actual social graph, is the cake pattern. This is used for dependency injection. It's helpful, again, providing code reuse, makes it easier to modify. So I have 3 slides with examples, and they're actually all somewhat related, but I don't actually expect you to follow along in too much detail. The third one's really the interesting one. So then we have actors. Again, so here's a cluster manager component, which you can see is being extended in the cake pattern example. And so it has a cluster manager, which is an actor. You can also see our use of case classes, which we use heavily for these types of nodes. And then some of the sealed traits make things easy to find. But here's the code I really want to talk about. So this is, I think, pretty cool. I did not write this. Chris Conrad, I think, wrote it. It's a cool code snippet where we can show some of the cool advanced features of Scala. So here we have the Zookeeper cluster manager, and it has so we've queried the parameters that it takes. And the second one is a function that we're passing as a parameter. And you note that it's called the Zookeeper factory. So Zookeeper in the Java interface doesn't have a factory method. And if you want to make one, you have to do a lot of boilerplate. here we can just use this function that protects it, and then we use implicits so that you have the function defined here. You can go down later in the file and find this implicit default zookeeper factory, which will be automatically used unless something is specified instead. So it's using basically a very simple function as a factory method. And if you want to write this in Java, you would have a lot more boilerplate to get this. The other advantage is for testing. It is extremely simple to substitute. You want to call this with a different zookeeper, say a mock zookeeper factory. Then all you have to do is change that parameter. So now, if you want more info on Norbert, Chris Conrad gave a talk at Scala Days in 2010. There's the talk and the slides are both available. It's available on the LinkedIn SN8 projects. You can find a bunch of our open source projects there. Again, the GitHub. Ray's going to talk now about some of the, okay. Yes, anyone have questions on this? I guess we'll do split arc. Yes. Yes.
I have a question. Which actor framework are you using? Actor implementation? Is it Akka or is it Scala?
I think Scala actors.
Okay. So it's old code.
Yes. A lot of this code is somewhat old.
About 2 years.
2 years,
Two,
yeah.
2.7.
2.7. Yeah. Any other questions? Okay. Yes.
So unrelated to Scala, but what do you guys use for graph partition of the social graph?
For the partition the graph?
Yeah. If you.
So I don't know. So the Norbert provides a number of different methods for partitioning and doing the load balancing. I don't know if we can talk about the actual specific one that we're using, but that has a bunch. It has some hash functions, some random functions, some things of that sort.
So you basically hide the potential latency. Well, basically, you hide the fact that a node might be on a different physical machine by using
Right.
actors, right?
Yeah.
I'm not sure who was supposed to.
So Norbert is allowing you to send messages to different machines through the actors, through the zookeeper is
Okay.
handling that.
Okay.
So Ray's now going to talk a bit about some of the ways that we handle concurrency. This is actually from code that's related to our social graph, the actual distributed graph itself.
Thank you. All right. My name is Ray. I have worked at the social graph team for almost 4 years. We basically adopted Scala. Everything used to be Java. We basically adopted Scala maybe little bit over 2 years ago. I'm going to talk about a few features that we used that I personally really liked. It really makes programming much easier and enjoyable. One thing that we use pretty extensively in our system is the copy on write to handle read and write, concurrent read and write. So basically, instead of having a complex read and write lock, every data structure in our system is mutable. When there's a writer come in to update the data, the writer will be in charge of creating a copy of the existing old data. And we have only one writer thread. So in such a system, you would never have a read or reader or writer never block each other. And as a developer, as far as you follow these two rules, that you have just one, all of your writer goes through the same thread. And if you are introducing new data structure, you're making it immutable, then your read and write are safe in the system. So here's one example. A simple example kind of demonstrating the idea. Let's say we have a tree structure like that and in the blue nodes. And we are adding one additional node, 8 under 6. In this case, in this scenario, what the writer does is it's going to make a new copy of 6 all the way up to the root. And then all of these newly created nodes will link to the the newly created node will refer to the part of the tree that hasn't been changed. So after the writer make the changes, you will end up having two roots of the same tree in the system. The existing older reader will have references to the older node, but any new reader that comes in will have references to the new root. After all of the existing reader finish reading the data, basically the old tree node, the 6, 3, and 1 in the old tree, it doesn't have any references referred to them, and the Java garbage collection will help take care of reclaiming that memory space. So this is basically how we handle read and write in our graph. So another feature that we use pretty extensively is the mixing. So in our graph, we have edges that represent different kind of entities and different kind of relationship in our system. And each type of relationship consists of a set of features. And these features match pretty nicely to the trait in Scala. In our implementation, we can whenever we can use these traits, mix and match to create different type of edges. And Java has interface, but the one problem that Java has is it doesn't support multiple inheritance. And using traits, we can actually group the interface with the actual implementation that tied specific to that trait, and then mix and match, creating a new instance which represent different type of edges. The last thing I wanted to talk about, which is kind of one thing that we learned during our course of building a large-scale social graph with Scala is even though Scala provides a very powerful library and it's really it makes programming very quick when you are doing some type of scripting type of things. But when you are using it to store large-scale data, you probably want to make sure you don't overlook the object overhead. So in our practice, we use a couple of different tools to monitor the heap usage for the Scala implementation. And I personally like JMAT and JHAT because it comes with JVM. You can pretty much use it from any system. And the I assume everybody knows, like JMap is the one that you can take a heap dump. JHAT is you can basically do, you can look at the your heap distribution and you can do like some simple query to query your object usage. And there's another tool, memory analyzer, which provide a little friendly, user-friendly graphical interface. So what I'm going to talk about is the implementation, Scala implementation for a hash map. The Scala hash map, it uses a try map underneath it. So initially, basically, you have a leaf map object if you only have like one key value pair in your map, you have a leaf node, which is the hash map 1 implementation, and then instance, and then when you are adding an additional key value pair in your system, you end up having this try map, which link to a bunch of hash map 1 instance, and then when you're adding even more, the try map split, and then there's another layer of try map linking to the lower layer try map. So in the end, you have a tree, and at the bottom layer of the tree, you have the actual the hash map 1 instance holding your key value pairs. So as you can see, the actual data is actually just exist in the leaf layer. All of the other data, all of your try map and the hash map 1 is the supporting data structure for your system. So I measured in a 64-bit JVM for the hash map 1 instance. It takes 44 bytes, and here's a breakdown of where does the 44 bytes goes. 44 bytes is not a lot of data, but if you end up using this hash map to store int-to-int mapping, let's say you have a code sniff like that. Basically, I'm just storing 1 million int-to-int mapping to the Scala default hash map. Then what I end up, so this is a overview, kind of like a screenshot from the JHAT. Basically, only the integer portion is your data. Everything else is just the tree structure and the containers for your data. So as you can see, you basically have about 89 megabyte of data here. So for us, this is just the amount of the percentage of supporting data versus the actual data is a little too large. So we actually use this information to guide us to do more customization. And here, based on that information we got from this view, we try to change the way the default Scala map is created. We flatten out the leaf layer, making it a little bigger so that it doesn't just hold one key value pair. Instead, it holds an array of key value pairs, and we use the tree structure together with the leaf layer byte as to reconstruct an integer key. So this is just a customization for the int-to-int mapping. And after our customization, we are able to shrink down the same code sniff, taking a heap dump, is about using our customization is about 10% of what the default Scala collection would use in terms of memory usage. So overall, I think Scala, I personally like Scala because it's really concise, it's make coding very clean. But if you are dealing, especially if you are doing not memory intensive operation, you pretty much, it's very fast. But if you wanted to do anything a little fancier, dealing with large scale data, you might want to run everything in a heap profiler just to make sure that your data, you're okay with the overhead. Also, as a user converting from Java to Scala, I agree with what Mark said. It is a pretty steep curve, and the moment for me that I felt more comfortable with Scala is when I started doing this sort of customization and looking into the source code. So as a suggestion, if you're new to Scala, I would highly recommend look at. I think there's on the document there's a linkage to the source. Once you are familiar with the actual implementation, a lot of these. I think it's a lot faster to use this to adopt Scala. Questions?
If you have like 1,000 threads, and each of them are handling like a million entry hash map, and you're following this immutable regime, so each of them each thread has at least one copy of an immutable hash map, and they're all trying to update them. Doesn't that mean you have an unthinkable number of copies of these hash map structures? Or did you actually reach down into the hash map structures so that you're doing structure sharing and stuff in order to accommodate that?
So in our usage, we actually have only one writer thread. So we have like lots of threads, but most of them are readers.
And they always just fetch the most recently written one.
Right.
I guess that would fix it then.
Did I get the question? Okay. So, sorry, did I answer your question?
Yeah, that's it.
Okay.
I wasn't thinking good.
There you go.
So I'm wondering, looking at this, actually, it's very interesting looking at this implementation. Some people raise concerns that the Scala standard library is written by a bunch of graduate students and it's a bit amateurish compared to Java standard libraries, and it's about time, I'd say, bring some people to sort of rewrite it. I wonder what's your opinion based on your deep examination on performance of Scala libraries.
Sorry, I'm not sure I get the question.
So the question is, would you say that Scala standard library is a bit amateurish and needs some serious rewriting in order to bring it up to performance expected in sort of production environment?
I would. So I wouldn't say that. I think our use of Scala is in a pretty extreme case. And also, when I was researching, so I did a lot of work like that. So when I was kind of looking for a very efficient version of Scala implementation, I think that was at least a year ago. I have seen many people contributing to Scala for a particular type of map like that. So I think in this particular case, if you are creating like a object map, these overhead may not be a lot for you comparing the size of your data. But if you're doing like integers, even in Java, it's the same thing. Like there are a lot of Java implementations try to reduce the object overhead for similar things like that. I think there are some, I think a fast util library or something like that. There are a bunch of optimizations like that. But in this case, because Scala, in this particular case, is kind of extreme because it has like a tuple and then like object overhead and all of that. And I'm just taking an extreme case as example. And the other thing is, as a new Scala user like myself, I've been using Java for a long time, so normally when I'm programming in Java, conceptually I have a good idea how much memory everything uses. And in Scala, because it's so expressive and concise, a lot of the times I felt a little lost in control in terms of what exactly it's doing. That's why I highly recommend. I think for me, the breakthrough from my personal experience using Scala is when I started doing some of these customized library, when I dig into the actual source code.
Can you recommend any performance assessment software yeah.
So like I mentioned, I use JMap and JHead a lot. It's really simple. It comes with JVM. It's just one command. Normally, if your heap size is not too big, you can you run your thing. Or like in this case, right? Because Scala, because Scala has this console, you can just copy paste your coding into the console and attach a debugger, and do the heap dump with the process ID using JMap and bring it up using JHead. And it gives you a good amount of information. If you wanted to dig a little deeper, sometime because the default tool that comes with the JVM is a little, the formatting is very basic. So if you wanted to do more advanced searching, either your kit or memory analyzer could be a pretty good tool. All right, I guess I'll introduce the Joe. He's from our Kafka team.
Hi everyone, my name is Joel, and I've been at LinkedIn for nearly a year, and that's about how long I've been working with Scala. And I'm going to talk about Kafka. Kafka is a distributed publish-subscribe system, and I'm going to talk mostly about Kafka. I do have a few code snippets and interesting experiences at the end, but I'd like to spend more time on Kafka itself because it's a good example of a key piece of infrastructure that was built almost completely in Scala. So just for some background, most of you may know this, but a publish-subscribe system, this is what it typically looks like. You have a bunch of producers that send messages to one or more topics, and you have a bunch of consumers that subscribe to these topics and consume them over time. And there are various semantics that you could potentially need. Some applications might need every message to be consumed at least exactly once by at most one consumer. Some would need exactly once by end consumers. You could have push models, pull models, and so on. And I'm going to talk about LinkedIn's usage of Kafka. And although this really applies to any company, any website that deals with a sizable audience. And at LinkedIn, we use activity tracking. It's a crucial ingredient in a number of LinkedIn products. And we use user activity data to power recommendation systems, to optimize ad displays, and so on. We also need a very streamlined mechanism to build dashboards to monitor our production environment, and that means server and service metrics. And although this is not crucial to the business metrics, it effectively translates to that as well, and it is important to be able to have near real-time access to operational metrics. And before Kafka existed, at LinkedIn, we had a pretty simple event-based logging system. So, and as the site grew, as our member base grew, it revealed various issues. It had scalability issues, and also I think the biggest drawback was the lack of real-time data access to this tracking data stream. And that's why there was a real need for something better. And in evaluating alternatives, at one extreme, there were these messaging systems that offered message queue semantics, and they provided very low latency. However, they didn't quite provide the sustained throughput that was required. And this was largely due to runtime overheads as a result of implementing features such as secondary indexes, which we did not really need at the time. And at the other end, there were log aggregation systems, and these basically take a bunch of messages and pump it into HDFS, and they offer very high throughput, but they don't have direct support for real-time incremental consumption. And Kafka sits somewhere in between these two extremes. It basically allows a bunch of producers to send messages to a distributed set of brokers, and messages are persisted there, and consumers can pull them at very high throughput. And it's also scalable elastically. You can add more brokers as you need. And I'm not going to go into too many low-level details of Kafka's design. I'm going to focus more on its usage and certain aspects of its design that allow it to be efficient. So in a typical Kafka cluster, you have one or more Kafka servers called brokers, and they are registered in Zookeeper. Zookeeper is basically a distributed coordination service, and you have a bunch of producers that could discover brokers either through Zookeeper, or you could place a hardware load balancer in front of the brokers. And consumers also register themselves in Zookeeper and subscribe to topics and consume the messages of the brokers. So we also have the concept of consumer groups, and basically what that means is for any given, if a consumer group subscribes to a topic, each message in that topic is delivered to at most one consumer in that consumer group. The messages themselves are stored at the broker, and we use a very simple and efficient storage layer for that. So basically, at the broker, topics are divided into partitions. These partitions are spread across all the brokers, and it is the unit of parallelism for consumers. So I mentioned consumer groups in the previous slide. So each consumer in a given group can own at most one partition for consumption. So if you want to have more parallelism, you would need more partitions. And the partitions themselves are contain flat files called event logs, and they contain the actual messages, which means we can address messages by their offset in the log file. Now, the log file approach actually allows us to provide an SLA-based retention time, and that means consumers could potentially rewind their consumption. So because messages are addressed by offsets, as long as a consumer keeps track of these offsets, a consumer can rewind to an earlier offset as long as that message is still present on the broker. We also have data integrity checks within each message. And another point is when consumers when they issue fetch requests, it effectively translates to linear scans over these files. And also producers, when they send their messages, these messages are just appended to the end of the file. So the access pattern is very linear. And that is good because consumer fetches become efficient, mainly due to the use of the page cache in the OS, and also because the messages are checksummed. They can be verified independently at the consumer. So all we have to do at the broker, which hosts the message, when it receives a fetch request, we just read from the file and directly transfer it to the socket without any intermediate buffering in the application. And another aspect of both the producer and consumer is that these requests are batched, effectively batched. And that amortizes the cost of network communication between the clients, that is consumers and producers, and the Kafka brokers. And messages can also be compressed, and that cuts down quite a bit on throughput, improves throughput quite a bit, and even on the log files, messages can be stored in a compressed format. So just about every service and front end in LinkedIn sends tracking data to Kafka, and there are several real-time and offline use cases for this tracking data. For example, security systems feed off of this tracking data to detect and respond in near real time to fraud or abuse. And another a good example of a real-time use case is one I mentioned earlier, and that's systems monitoring. So all the production services and servers send metrics information, and this could be either low-level CPU stats or load average, and so on. It could also be application-level statistics, and these are all sent to Kafka brokers, and we have tools that consume these topics in near real time and generate these dashboards. So we have near real-time visibility into how healthy our production environment is, and we can watch notable events such as deploying a new service and so on. And that's a very powerful tool, I think. Another use case, more at the application level, is the news feed. So I believe this is powered by consuming user activity within your network in near real time. We also have the more traditional use case. So Kafka can broker this tracking data that is eventually loaded into Hadoop and our data warehouse. And this really fulfills the more traditional use case for data analytics that's done offline. I think one additional use case that we benefit from, and it is perhaps a deficiency of more traditional data warehouses, is that the data warehouse tends to be batch-oriented, so you don't have real-time incremental access to curated data. So what we do is, we don't do this across the board, but we can publish back some of this decorated data back to production clusters, and this data is available to services and applications in production to use as well. So a few usage statistics. It's pretty high volume. We see about 10 billion events per day, and this is both user activity tracking and service metrics. That means around 3 terabytes per day of data shipped through Kafka. And we have at peak, we see about 172,000 messages per second. And we have about 10,000 producers and consumers connected to our brokers. And this is with I think 8 Kafka brokers in total. So with that, I'm going to go into a few interesting experiences we had with Kafka. So Kafka is written almost exclusively in Scala. I think we're at about 15,000 lines of code or so, and that's excluding tests. We do enjoy the fact that it's faster to develop in Scala. It just cuts down a lot of boilerplate code, I think. That said, I wouldn't say Kafka is a power user of Scala. It does use collections fairly extensively, and we use zips, flattens, and maps, and so on. And I think it yields code that is pretty concise and readable, and less prone to bugs in logic, and that is most of the time. So I don't. In the following slides, I'm going to go through a few interesting bugs that we saw, mostly due to our own mistakes, of course. But I think some of the language features made it a little bit hard to actually see what was going on. So here's a little bit of a method in the producer called serialize. So I had mentioned that the producer batches requests to send to the broker, and these events that are sent actually need to be transformed into Kafka's internal message format, which is called a message set. So basically what this function takes is a map that takes a map that is keyed by topic and partition, and the value is a list of events that need to be sent to that partition, and it returns another map which contains those events converted into a message set. So that's what lines 6 and 7 are doing. It's using a map. So by the way, the map function, all it does is given a collection, it returns a new collection which is created by applying the given function to each element of the original function. So in line 6 and 7, we're basically converting each event into a Kafka message. And in lines 9 through 14, each of those lists of messages are converted into a single message set. And in line 16, we extract the original list of topics and partitions. And in line 18, we zip them together. And what zip does is it takes two collections and it joins together corresponding elements from both collections. Now, what we expected this to do was to take the given list of events and return a message set for each topic and partition. But the problem in this code is that the underlying maps that were zipped together were actually derived from two different maps. And it turns out that the ordering of the keys can end up being different. So the end result is that messages that were intended for one topic ended up going to another topic, and that pretty much completely broke Kafka's functionality, and this actually went to production and took some time to understand what was going on. But again, this is a programming bug, but it's something that was not obvious even after code reviews. And there is a Jira in Apache. Oh, I forgot to mention, I should have mentioned it at the beginning. Kafka is an Apache project, incubator project right now. And this issue is described in Kafka 107. So another example that happened, I think, last week was we were seeing some corrupt produce requests, and we wanted to debug what was going on. So we searched through our code, and we found this method that we thought would help us debug what was going on. So we added the try and catch block around the original code, and in the event of an invalid message exception, we would actually serialize that request onto disk, and we could go later and debug and look into that file to see what was going on. Now, we deployed this, and then nothing happened. Nothing was getting serialized. Well, the problem here was that we put the try-catch block in the wrong function. This handle for function really was not the place where the actual request was being handled. This was a function that basically, given a request, would find out which handler to use and return that handler. So in this case, the point is that these cases that you see, they looked like function calls, but really they were not. They were just returning a handle to a function. And so this is blatantly a programming error, but the point is that we didn't notice it even after several code reviews. And I guess this means we have a lot more to learn about Scala. We're still relatively inexperienced. But we do appreciate some of the expressiveness that Scala offers, and that actually it's a bit difficult to use it because in the sense that even though Kafka is written almost exclusively in Scala, most of the clients we have at LinkedIn are Java-based, so we want to support an API that's fairly consistent between Scala and Java. And this is an example of a proposal for a consumer API that we had a few months ago. Basically, it takes a map of mapping topics to stream configs. So if you want to consume from a bunch of topics, you would provide the topic names in a map along with the configuration for the stream you want to consume from. And I think some code will make it clearer. So you could have a stream of integers, or you could have a stream of richer objects called activity objects, and you would provide a decoder for each of them, a suitable decoder that converts from the internal Kafka message to the final type. And you can iterate over your streams without having to do any explicit decoding. So it's a fairly convenient API to have. The point here is that the covariant declaration at the top allows you to actually mix the types. So you can have integer streams, you can have activity streams, you could have some other type stream, all in a single call to create streams. Now the problem is Java doesn't really allow you to do something like this. So sometimes we are compelled to compromise on elegance and expressiveness just to keep the APIs consistent. And that's pretty much what we ended up doing, and this is discussed in Kafka 3. So we have a much simpler API that is a little bit more limited, but it's mainly to keep the APIs consistent. And I think I was, this is a really, really trivial bug, but I think it's a good example of one of Scala's features that helps in avoiding logic bugs. So we had this loop that handles producer batches. So what it effectively does is, while running, while it's not shut down, it polls the producer's queue. If it has any event to send, it's going to add it to another internal buffer called events. And if a timeout is reached, or if the batch size is reached, it actually handles the events, that is, sends it to the brokers. And the corner case to handle is when you are shutting down, that is, if running is false, you return the last batch of events, and that is subsequently sent before actual shutdown. The problem in this code is that the running, you could break out of the loop without actually checking to see if there's anything new in your producer queue. And we fixed that by using stream continually. And to be honest, this code is a little bit harder to read than the previous one, but it does make it clear what your exit condition is, what functionality is being repeated. And the problem in the previous code is there were external buttons to exit from the middle of the loop. And this code does effectively the same thing. It fixes the bug that was there before, but it is also, as you write this code, it'll become, you have the assurance that it does what you expect it to do. So I think with that, I'm pretty much done. We have successfully deployed it in production at LinkedIn, and there are a number of other companies that use Kafka. That includes Twitter, Tumblr. There are a few others. We have a powered by page on our Apache wiki that describes some of the other companies' usage. 07 was released a few months ago. It contains the compression support and a mirroring feature, and 08 is coming this summer. And this is our team. 5 of us are at LinkedIn, and there are 3 committers outside. And feel free to visit our site, and we have a mailing list. It's pretty active these days. Thank you.
I was wondering on that example of kind of an impedance mismatch between the Java and Scala APIs, with the covariance example, that I wondered if you had considered having like a Java, just putting a Java facade over it rather than dumbing down the actual Scala code, putting a simplified Java facade for Java callers. So you could still access, from Scala, you could still access the covariant code.
Sure, yeah, we could definitely do that. In fact, that was one of the proposed ideas, but ultimately you would have a different API for Java users and Scala users. It's a choice anyone has to make. We just chose to keep it consistent, that's all.
It's a great presentation. I have actually two questions. One is the low level. I see you use streams, and I tried to use streams in some of my code. It's kind of tricky if you hold the head of the stream, it can run out of memory easily. I wonder how you debug these kind of situations. That's sort of a low level question. And the high level question, from a use case, it sounds like you would benefit from a real-time in-memory system like Storm or Spark, because you mostly run reporting on this, right? On 3 terabyte, you can hold it in RAM in the cluster. You can run like real-time reporting of all kinds of so I'm just curious, what would you say to a typical use case? When would you use Kafka when, let's say, Spark or Storm is not good enough? How would you sort of position these two use cases?
So I think the first question, actually, can you do the first question
I'm
again?
just wondering, I've seen you use streams, and I found in my usage, streams are hard to bug, because if you manage to not release it, if you hold the head of the stream, you run out of memory. So I'm just curious how persistent the stream usage, how efficient is stream usage in Kafka. What would you recommend using streams?
Sure. So we haven't really encountered any issues. That said, how do we debug things? So Kafka is a heavily multi-threaded application. So I don't think any of us in our team actively uses like live debuggers and things like that. We pretty much use log messages. Yeah. And the other question, Kafka really sits somewhere in between. So we did experiment with, by the way, this was, I think, before my time, with low latency messaging systems, and a lot of them keep their messages in a in-memory buffer. And the thing is, it doesn't do all that we need it to do. So we need to be able to support a very large number of topics. I think we have of the order of 300 topics right now. And if you take all of them in aggregate, and it's just not possible to put them in memory. Now, it's really intended to be near real time. So you have the capability of consuming messages in near real time, and you have the more traditional offline use cases. I've heard of Storm at Twitter. I'm not very familiar with it though.
In fact, I use all three systems, and even Twitter uses a common pattern weighted, for example, in Kernel, which is similar to Kafka. And so they use
There's a microphone for people who want to talk. If you have something to say, talk over. So first question is for the Kafka performance issue.
What's it?
For performance,
Mm-hmm.
you say performance is very, very good.
Mm-hmm.
Could you compare with honest queue with JBoss?
So I don't have the numbers here, but we do have a paper that's linked off of our Apache page that does compare it with some other messaging systems. I don't have those numbers with me right now.
Have you compared with the honest queue?
No. Hornet queue.
Honest queue with
No.
JBoss?
No, we have not. It's
Because-
with ActiveMQ, yes.
Yeah, because both use Netty underneath
Mm-hmm.
for the asynchrony
Yeah.
issue. So
So I
that
think
is your major competitor.
So I think the last performance comparison that was done was a year ago or so, and that's described in we have a NetDB paper. We did not do a comparison with HornetQ.
Okay. The second question: have you compared with other WebSocket message block?
Such as?
WebSocket message block, some
No.
protocol.
No, we have not.
Okay. They have another bigger candidate for event loop.
Yeah, we haven't done that.
Okay. Thanks.
Kafka was a scary writer. Why did you guys choose that name?
Yeah, I think yeah, I think Jake Krebs names his projects after whatever he's, something to do with whatever he's reading. I think Voldemort was also named as a result of him reading, yeah, I think Lord of the Rings, yeah. Any other questions? All right, thank you.